Okay, so we are now going to begin a unit on probability. I'm sure you've probably heard of probability before. It has to do with obviously the likelihood of something occurring in a specific situation. So I just want to start by going over a little bit of vocabulary. So, sample space. A sample space is talking about a collection of all possible outcomes of a chance experiment. So, for example, when you flip a coin, your sample space is heads or tails. If you roll a die, your sample space is 1, 2, 3, 4, 5, or 6. Okay, so all the things that could occur when you're actually, rolling that die or flipping that coin or whatever situation, that's your sample space. An event is the specific thing that occurs. Okay, so out of all your different options, what specific event happens in that particular situation? So, given event A, the probability of A is you add up the total number of times that A can occur. So, for example, let's take the coin flip for a second. And let's say the chances of heads is what we're trying to work on right now. There's only one way to be able to land on heads, okay? Out of two possible outcomes, heads or tails. So in that situation, the probability would be 1/2. So you take all of the ways that A could happen out of all the possible outcomes in your sample space, and that gives you the probability of something occurring. So for example, let's take rolling a die. If let's say we wanted to find out what are the chances of landing on 4. Well, how many different, like if you take a die, how many sides have a 4 on it? Only one side has a 4 on it. Okay, how many sides are there on a die altogether? 6. So the probability of getting landing on 4 when you roll a die would be 1/6. Okay. Okay. So now if I take a look at example number 1, determine the sample space. So a card bag contains 6 cards. 4 of these cards are blue with the letter A, B, C, or D written on them. 2 cards are red with the letter E or F written on them. So we first want to list out, well, what are all the situations that could occur? Okay, blue and A, B, C are not separate from each other. You'll notice you have a blue card that has an A on it. That's why you see blue A as the first thing in the sample space. We also have a blue card that has the letter B on it, a blue card that has the letter C on it, a blue card that has the letter D on it, and that's the end of the blue cards. Okay, so now when I switch over, I next have red cards. I have a red card with the letter E on it, and I have a red card with the letter F on it. Okay, so this is all, like if I put that bag down with those 6 cards in it, and I pick a random card out of it, these are the only 6 things that could occur. So let's talk a little bit about the probability of or the likelihood of picking, each of these different situations, and then we'll talk a little more about what kinds of probabilities we could have. So if you look at the first example, it says determine the probability of picking a blue card. Okay, so what you're going to do is you're going to add up how many blue cards do we have. We have 4 cards in total that are blue. So 4 blue cards out of how many cards altogether? 6 cards altogether. That means 4/6 is the probability of that occurring. So you could leave 4/6, that's totally fine. You could also reduce 4/6 to be 2/3. Or if you want to list it as a decimal, it could be 0.667. Just so you know, all probabilities you should be rounding to the nearest thousandth, 3 decimal places at least. If you want to go beyond that, honestly, that's fine, but at least 3 decimal places. Now, you'll hear sometimes when it comes to probability, people refer to it as like a percentage, like this is a 67% chance of occurring, but realistically, probabilities actually are only on a scale between 0 and 1, okay? So that percentage is a way of expressing it, but you should really always think of probabilities being a value between 0 and 1. If something is a probability of 0, that means that it's impossible, okay? So for example, if I flip a coin, what is the chance that it's going to land on heads and tails at the same time? That's impossible. That's a probability of 0. Okay? Then if you go all the way to the other side of probability, if you get a probability of 1, that means that it's definite. So for example, what's the probability that you're watching a math lesson right now? You are watching a math lesson right now. That's definite. That's a probability of 1. So I would usually put 0.5 in the middle as kind of like the boundary between where things are less likely to occur and more likely to occur. But realistically, you just have to kind of compare 2 probabilities. Whichever one is closer to 1 is more likely. Whichever one is closer to 0 is less likely. Okay, so again, it's okay to use the percentage to describe the probability, but you should really always think of it being between 0 and 1. And I just want to clarify, that means you can never have a probability that's more than 1, so you can't have a probability of like 1.25, and you can never have a probability that's ever less than 0, so you can never have it be negative or anything like that. So, if you take a look at number 2, what's the chances that if I pull a card out of this bag, the card has an A on it? Well, if you look through all your cards, there's only one card that has an A on it. So 1 out of the 6 cards, 1/6 is my probability, or if I want to put this as a decimal, 0.167. Okay, again, you can think of it in your head as like a 17% chance, which hopefully in your mind that means, okay, that's probably not very likely. But at the same time, you should really always remember that probabilities are going to always be between 0 and 1. Okay, what's the probability that I pick out a red card? So remember, there are 2 cards that are red out of those 6 cards altogether. So that comes out to be a probability of 2/6 or 1/3 or 0.333. So we're going to now talk about something called complements. And the complements are going to you're going to see like you're going to connect in your head with the word not. So this is saying, what's the probability that if I pick a card out of this bag, the card is not going to be red? Okay, so if you think about it, I have 2 cards that are red, right? If you look up here, that means I have 1, 2, 3, 4 cards that are not going to be red. So I could say, all right, that's going to be 4 out of 6, or 2/3. Or another way that I could look at it is to use the complement rule like I have below. Okay, the reason why I have this complement rule is that the probabilities, okay, of all, I'm sorry, I know I swear I can spell. We did it again. The probabilities, okay, of all events in a sample space add up to 1. Okay, add up to definite. So, for example, in this situation, I have blue cards and I have red cards. If you add up the chances of blue plus the chances of red, since those are the only 2 options in our sample space, you have to have those all add up to be 1. Okay? Or if you flip a coin and you get heads or tails, if you add up the chances of heads plus the chances of tails, those 2 probabilities have to add up to be 1. So again, when you add up the probabilities of all events in a sample space, they add up to be 1. So if you're being asked to find out what's the chances of something not occurring, take 1 minus the chances that it does occur, and that's going to help give you the not probability. Okay? And vice versa. If I want to know the chances of A occurring, I could do 1 minus the probability of not getting A, and that could also be the way of calculating instead of adding up how many times it happens out of the total number of outcomes. So an alternative way you could have looked at number 4 is you could have said, if I want the probability of not getting a red, do 1 minus the chance of getting a red. 1 minus the chance of getting red was 1/3, and you can see you end up getting the same probability either way. Okay, so I'm not saying you have to use the complement rule, but it might be helpful in some situations. And I do just want to re-emphasize that idea that the probabilities of all events in a sample space have to add up to be 1. Something has to occur. That's basically what that's saying. You may say sometimes for the not probability, something that kind of looks like an exponent with like a C as the exponent. It's just a way of referencing the complement. I don't think you're going to really see a lot of that in what we do, but I just wanted to make sure that you were familiar with the fact that that means the same thing as the probability of not A. Okay, so this is where we get into territory where probability gets like a little more confusing just because you start getting into what we call compound probability, and there's a lot of keywords, but the good thing is we're going to be going over these keywords again in the next couple of days, so this is just a preliminary introduction to how you do some of these compound probabilities. So let's start with the word or. When you see the word or, I want you to think add, okay? So if it says probability of A or B, which sometimes, by the way, could also be represented as the letter U, I want you to think of that as the probability of A, or, again, think of it as add, the probability of B. Or means add. Now, there's a key word that has to be true in order for you to be able to actually do your calculation this way, and that's the word disjoint. In order for you to be able to just strictly add probabilities, if you're doing this or this union, they have to be disjoint. So what does disjoint actually mean? It means that they have no outcomes in common, or a better way maybe of thinking of that is that they cannot occur at the same time. Okay, so you want a perfect example of events that are disjoint. When you flip a coin, can it land on heads and tails at the exact same time? One coin flip, can it land on both sides? And the answer is no. So that would be an example of disjoint events. So for example, if it's, if I'm flipping one coin, what are the chances of it landing on heads or tails? Because of the fact that landing on heads and tails cannot happen at the same time, these are disjoint events, so I can just add their probabilities together. I could take the probability of landing on heads plus the probability of landing on tails. That would be 1/2 plus 1/2, and in this case that adds up to be 1. I do want to kind of point out that goes back to what I was just saying before. If you take all the probabilities of the events in a sample space, they have to add up to be 1. When you flip a coin, it's either going to only land on heads or on tails. So obviously you see when I add those probabilities together, they add up to be 1. Okay, intersection. So intersection means and. That's what you should be thinking of. So when you see the word and, I want you to think multiply. Okay, so and that can also be represented, by the way, as this and looking symbol. I kind of think of it almost like it's an A. That's kind of how I think of the intersection symbol. But again, and again, we're going to work on these over the next couple days in different ways. But when you see and, I want you to think multiply. So if I want the probability of A and B, I take the probability of A, replace and with multiply it by the probability of B, and that gives me my final probability of these two things occurring together. Now, there is a keyword that's associated with this that has to be true in order for you to be able to multiply, or you're going to have to do something else, and that's the word independent. Independent, if you think about, when somebody is independent, they don't lean on anybody else or they're not affected by anybody else. Well, that's what independent means in terms of probability. Event A does not affect the outcome of event B. Okay, so perfect example of independent events. If you were to roll a die, okay, and at the same time you were to flip a coin, is what happens with that die going to have any impact on what happens when you flip that coin? The answer is no. No matter what you get on the die, when you flip that coin, it's going to be a totally separate outcome. Those are perfect examples of independent events. So that means that if I want to calculate the probability of getting a 6 and at the same time flipping a coin and landing on heads, then what I can do is I can say the probability of 6 and becomes multiply. I take the probability of, flipping a coin and landing on heads, and I can multiply their probabilities together. The chances of getting a 6 would be 1/6. The chance of landing on heads would be 1/2. So there's a 1/12 possibility that if I roll a die and I flip a coin at the same time, that the die is going to say 6 and the coin is going to say heads. Okay? So again, if I don't have independent events, I cannot just multiply my probabilities together. There's going to have to be something else we're going to do. And again, we're going to explore independence over the next couple of days in a variety of different ways. Okay? So kind of recapping, think or as add, think and as multiply. But again, remember, there are specific conditions that have to be true for you to be able to use those formulas, or we're going to need a different formula. So let's do a little bit of practice with this. It says a traffic light on Pigeon Hill Road intersects with Wolf Hill Road, can either be green, yellow, or red. What events make up the sample space? So think about it. You're driving up to a light. What could occur? You could either land on green, like, the light could be green, or the light could be yellow, or the light could be red. There's no other things that could occur with those lights. Okay, obviously don't think about arrows. That's not being included this time. So the first question is, are these events disjoint? Can they occur at the same time? Can the light be green and yellow at the same time? Can the light be yellow and red at the same time? The answer is no. They're not going to happen at the same time. So yes, these are disjoint. Okay? They cannot occur at the same time. Okay? So that means when you go to eventually adding probabilities together, you'll be able to just add probability of one thing plus the probability of the other without having to worry about it using a different formula. So now, disjoint and independent, sometimes people get confused with those key terms. So like I said, don't stress if you have a hard time. We're going to be going over these key terms again in the next couple of lessons. This question says, are these events independent? So the idea is, does the probability of getting, a green when you show up at that light affect the probability of getting a yellow when you show up at that light? And the answer is actually yes. because of the fact that the light can't be green and yellow at the same time, for example, the chances of it being green affects the chances of it being yellow. Therefore, these are not independent. Okay? So the chance of the light being green affects the chance of the light being red or yellow or whatever it happens to be. Okay, those probabilities affect each other. So what impact does that have on us for our calculations? When you go to do an and calculation, that's an intersection, you're going to have to be careful to make sure that you don't do it like just multiplying your probabilities together, because these are not independent. We'll have to think of things in a different way. Okay, so it's determine the probability of the given events. It was determined that the probability of getting green when you show up to the light is 0.35, and the probability of the light being yellow is 0.04. So think about our sample space right now. We only have green, yellow, and red. And when you add all those probabilities together, what do they have to add up to? They have to add up to be 1. So if I want to find out what the chances of it being red are, basically what I'm going to do is I'm going to find out what's the chance of it being green or yellow, and then I should have to just subtract that from 1. So what's the chance of getting green or yellow? Okay, union stands for or stands for add. Because these are disjoint, I can just add my probabilities together. So I take the probability of the light being green and the probability of the light being yellow, and I can just add those together. 0.35 plus 0.04 comes out to be 0.39. Okay, so there's a 39% chance the light is green or yellow. If I now want to figure out the probability of it being red, remember you can do the whole idea of the complement rule, 1 minus the probability of it being not red. Well, if it's not red, what is it going to be? It's going to be green or yellow. So I can do 1 minus 0.39 or 0.61. That's the chances of the light being red. So again, I just want to point out, if you now take the chances of green plus the chance of yellow plus the chance of red and add them all together, they have to add up to be 1 because those are the only 3 things in the sample space. Okay, do a little more practice with this or. So again, union, the U stands for or. When you see or, I want you to think add. Getting a green or a red can never happen at the same time, so they're disjoint, which means that I can just add the chances of the light being red plus the chances of the light being green together. The chance of the light being red was 0.61. The chance of the light being green was 0.35. So altogether, that comes out to be a probability of 0.96. There's a 96% chance that the light is red or green. Okay, so remember I had said that this little c that looks like an exponent, it just stands for the word not. So maybe you rewrite it like this. What are the chances that the light is not yellow? Well, if you think about it, if the light is not yellow, what is it? It's going to be red or green. So actually the answer is just the previous one that we just did. Okay, if it's not yellow, it's got to be red or green. So there's a 96% chance that it's not yellow. Another way you could look at it is to use that complement rule. If I want the probability of not yellow, I do 1 minus the probability of getting a yellow. So 1 minus the probability of yellow is 0.04, and that also comes out to be 0.96. So again, it's up to you which way you want to be able to do that complement probability. If you want to just strictly calculate it based on the other events or do the not probability type thing, it's up to you. Okay, so number 8 is going to be a little tricky. Remember I had said this kind of looks like an A kind of symbol, if you will. It's again talks about intersection, and when you see that intersection, that's and you want to think multiply, but unfortunately this was a situation where my events were not independent, so I actually can't just multiply them together. I have to actually think about this situation for a second. You're pulling up to a light. What are the chances that the light is both red and green at the same time? Is that even possible? Again, in the very, very, very small likelihood that you're looking at a broken light, maybe. But the reality is, if you get up to a light, it's not going to be red and green at the same time. So actually, this is a probability of 0, okay? This is a situation where these both can't occur at the same time. And again, that also kind of reinforces the idea that they're disjoint. They can't occur at the same time. So it's impossible to get red and green at the same time. So that's a probability of 0. Okay. I'm going to stick with this idea of these lights being red and yellow and green, and now I'm going to look at them over the course of a couple of days just to illustrate some examples of kind of independence where you can use that and multiply probability thing. So it says, let's look at the morning commute from Monday through Friday. What is the probability that you find the light red on both Monday and Tuesday? So you're saying I get the light being red on Monday and the light being red on Tuesday. So again, when you see and, I wanted you to think multiply, but that can only happen in a situation where events are independent. So the idea, or the thing you have to think about here is, does the chance of the light being red on Monday have any impact of the chance of the light being red on Tuesday? The answer is they don't. Okay, Monday does not affect Tuesday, and that's an example of illustrating these as independent events. Okay, so even though I know red, yellow, green are not independent of each other, Monday is independent from Tuesday, and that's why I can use that and multiply probabilities. So the chance of it being red on Monday is 0.61. The chance of it being red on Tuesday is 0.61. When I multiply those probabilities together, I get 0.372. Okay, so what does that mean? When you pull up to the light on Monday and then pull up to the light on Tuesday, there's a chance that the light is going to be both red on Monday and Tuesday of 37%. Okay, last question. What is the probability that you don't encounter a red light until Wednesday? Okay, so let's think about the situation. You drive to school on Monday, you drive to school on Tuesday, you drive to school on Wednesday, right? So think about the fact that it's Monday and Tuesday and Wednesday. Monday does not affect Tuesday, does not affect Wednesday, so and is going to mean multiply. And it says that you're not encountering a red light until Wednesday. So on Wednesday, there's a red light. But on Monday, it's not red. And Tuesday, it's not red. And is going to tell me to multiply. And again, Monday doesn't affect Tuesday, doesn't affect Wednesday. That's why these are independent of each other. The chances of it not being red, as we had mentioned before, was not red was 0.39. So there's a 0.39 chance of it being not red on Monday, and a 0.39 chance of it being not red on Tuesday, and a 0.61 chance of it being red on Wednesday. When I multiply all these together, I get 0.093, okay, or 9.3% chance that I'm only going to get a red light on Wednesday. What's the likelihood of that? Very unlikely. It means that as you pull up on Monday and Tuesday and Wednesday, it's very likely you're going to get a red light before Wednesday, okay? Because it's saying right here, if I only get a red light on Wednesday, there's only a 9% chance of that happening. Okay, thanks for listening.